So, now we are going to talk about the symmetries and the conservation principles in quantum mechanics. And so, what we mean by this is the following. Corresponding to a particular symmetry that is present in a given quantum system, there are certain quantities or certain observables which are constant of motion, and corresponding to that constant of motion there are some conserved quantities, which help us to simplify many aspects of a given problem. And these simplifications have helped us in developing various things that we will see along the way. And this is known to you from your first course of quantum mechanics, that a particular operator commutes with the Hamiltonian, then they share the same set of eigenfunctions, and they can be diagonalized simultaneously. So, these are basically the symmetry properties of that Hamiltonian, and corresponding to that some quantum number which is a good quantum number for that operator would remain conserved. We will explain that as we go along. And so, symmetries are usually of two kind. So, one is discrete symmetry so discrete symmetry. For example, such as inversion or parity, which is known as parity, which we will discuss, and maybe time reversal, etc. Whereas, there are other examples of continuous symmetry. Such as rotation and other things, such as even like translation, etc. These are so corresponding to this symmetry transformations, that is the system remains invariant under a particular operation, such as say translation or rotation. There are some generators which would be conserved, and it denotes a constant of motion. So, for example, if Hamiltonian commutes with a displacement operator, then momentum operator is constant of motion or in other words, this implies that momentum is a conserved quantity. So, P or K they can be called as good quantum numbers. So, here of course, we are talking about a linear momentum, and similarly the Hamiltonian. So, this is example 1 and this is 2. So, Hamiltonian commutes with the rotation operator which also can be read as generators of rotation, then the angular momentum is conserved. All right. So, Emmy Noether formulated a theorem which showed a relation between these conservation laws and the continuous symmetries that are present in the system. This you might have also read in classical mechanics in the name of Noether's theorem. So, here of course, we will talk about a few discrete symmetry principles. Symmetries, and they are namely say exchange of particles. Then of course, we will also talk about continuous symmetries and give a few examples which can be given. So, these are the discrete symmetries are exchange of particles and parity or space inversion and 3 time reversal invariance. So, let us see one by one, and we will only discuss this briefly. So, one is exchange of particles. For this, the fermions and the bosons have very distinct properties with regard to the exchange of particles. So, of course, let us talk about the fermions to begin with. So, they have antisymmetric wave function, what we mean is that we have a psi r 1 r 2. So, that is equal to minus psi r 2 r 1. And also there is Pauli's exclusion principle, and in a many particle system psi r 1 r 2 r I, r j and r n, this is equal to minus psi r 1 r 2 and r j r I r n. So, as we change the coordinates of one particle, or rather interchange the coordinates of two particles, that is r I going to r j and r j going to r I, it picks up a negative sign, and as we do it twice, it picks up another negative sign. So, it becomes equal to positive. So, what it means is that under even number of such transposition or change in the positions of particle, you will have a plus sign appearing, which is, so this is minus 1 whole to the power. So, this factor is like minus 1 whole to the power p, where p is the number of changes that are made, and so if p is even, then we will have a plus sign, and p is odd, we will have a minus sign. So, this is also as I said that it is also true in many particle sense, and this property is encoded, or rather these properties are encoded in Fermi-Dirac statistics. Which are developed by Pauli, Fermi and Dirac. This is in 1926. So, which basically describe the statistical properties of fermions. At low temperature. It is important to understand that this antisymmetric property enables writing the wave function in the form of a Slater determinant. Psi to be, there is a many particle psi that we are talking about, to be written Okay. So, what are Slater determinants? They are the following, that basically the wave function is written in terms of matrices, and we know that if we change the a row or a column, interchange a row or a column with another, then it picks up a negative sign, the determinant picks up a negative sign, and this is exactly what is required for the wave function of a many particle Fermi system. And also if two of the rows or the column becomes same identical, then the determinant vanishes, and this is nothing but the exclusion principle. So, these are encoded here, and they are of course for half integral spins. These are applicable to the half integral spins. And the statistics of course has very great applicability for, and applicable to large scale stability of Fermi systems and the existence of periodic table. So, let us talk about bosons. Which correspond to symmetric wave functions. So, symmetric wave function means the symmetric with respect to the interchange of particles, which means that psi r 1 r 2 equal to psi r 2 r 1, and in a many particle sense, a psi r 1, r 2, r I, r j, r n equal to psi r 1, r 2, r j, r I, r n. Of course, there is no constraint on the number of particles. That can occupy one quantum state. And of course, the important consequences are very well known. So, this was by Bose and Albert Einstein in 1924, when they were actually trying to formulate the correct statistics for photons, and immediately afterwards a Bose-Einstein condensation was proposed below a certain critical temperature for a given bosonic system, where all the particles will macroscopically occupy one quantum state. And of course, this is a buildup of particles in the momentum space corresponding to a momentum k equal to 0. So, that is the lowest momentum value which all the particles go and occupy below a certain temperature, and this was later verified in or experimentally observed by rubidium atoms and other bosonic atoms in 95. The main impediment was actually achieving a very low temperature, which could be done after many years of research in getting or achieving a low temperature, so that one can actually see condensate to form, and this was done by group in Colorado at Boulder in 1995. And then soon afterwards, a large number of groups have made these BEC, which is so this is called as a BEC possible in a variety of systems. All right, let's go over to the next symmetry principle, which is let us call it as a parity or the space inversion. So, space inversion and parity. So, space inversion or parity. And so, basically think of a parity operator. P, where P psi r equal to psi of minus r. So, so this is called as even parity when the parity operation, so parity operator operating on the wave function does not change the sign of the wave function. So, this is called even parity, and acting on this gives me a minus sign. This is called as the odd parity. So, the equation of motion is I h cross del p del t, it's equal to p h. So, if the parity operator commutes with the Hamiltonian, this commutator is equal to 0, and one says that the parity is conserved. Which means that the system has right left symmetry, or it has a symmetry if the spatial coordinates undergo an inversion or a parity operation. So, under this parity operation, R, the position vector that goes to minus R, P goes to minus P. However, J or L goes to J and does not change sign, goes to L, and simple reason is that L is equal to R cross P. If both R and P they change sign, then of course, the angular momentum operator does not change sign. J is of course L plus S, which S is the spin operator. So, in general, P psi of R equal to epsilon P psi of R. P square psi of R, if I operate it again by the parity operator, it gives me a epsilon P square psi of R. Now, this should be equal to psi of R. So, if we do an inversion once and then again we invert it about some certain fixed point or a certain fixed axis, then the system comes back to its original configuration. So, P squared of psi, P square acting on psi R will give me psi R. So, epsilon P will have values which are plus minus 1, and plus 1 corresponds to even parity and minus 1 corresponds to odd parity. So, plus 1 is called as even parity and minus 1 is called as a odd parity. Okay. So, let us talk about the third symmetry property, that is called discrete symmetry property, that is called as a time reversal symmetry. So, a time reversal transformation implies that t goes to minus t. So, it reverses the velocity of particles but does not affect positions. So, if R t is a solution of m R double dot t equal to minus gradient of V, which is a force, then R of minus t is also a solution of this equation. But the moment we include a damping term which is proportional to velocity, this does not hold good. So, a term since it is a damping term, I am writing it with a minus sign, but that is not required for this discussion. So, this is gamma and dr dt, which is basically a velocity term, does not validate the fact that R of minus t is also a solution of this, and thus a term like this actually breaks the time reversal invariance. And a practical example of this, not only a damping term like this, but in presence of a magnetic field or in presence of a magnetic field So, this is so it's like q into dr dt cross b. Again it doesn't time reversal doesn't hold. And hence we can say that the time reversed eigenstates, time reversed states are not eigenstates of the Hamiltonian, are not eigenstates. And this holds because of the loss of invariance under the reversal of velocities. So, if the velocities are reversed, then of course, the time reversal invariance does not hold good. And under this time reversal, r of course remain as r, p because it is proportional to the velocity, it becomes minus p, and because one of them change sign, the j or l they change sign minus j or minus l and so on. So, let us see what a time reversal operator is. The time evolution of a state is represented by I h cross del psi del t equal to h psi. Let a time reversal operator be represented by tau. Now, if this time reversal operator, namely tau, commutes with h, the Hamiltonian of the system, then we can write, see, we just want to introduce and tau is an unitary operator. So, I h cross del del t of tau inverse tau acting on psi, it is tau h, it's h tau inverse tau psi. Now, if we left multiply with a time reversal operator again, then this becomes equal to this. Now, since tau h equal to 0 because they commute, so a minus I h cross del del t of tau psi becomes equal to h tau psi. So, h so if the psi is operated by tau, so that still obeys the same equation of motion, and since then if we compare between these two, so a tau I h cross del del t of tau inverse, that is this part that is there. So, this is equal to a minus I h cross del del t. So, so that tells that if tau psi is equal to psi star, then the commutation relation is satisfied. Thus, time reversal operator is simply the complex conjugation operator. Okay. We shall in a while talk about discrete or rather the continuous symmetries. We have been talking about discrete symmetries, pardon me. So, we will talk about continuous symmetries and see some of the examples of continuous symmetries in real systems, and that is what would be the motive or the objective of the course. From now on, that will apply these concepts, basic concepts, to various fields of applied fields which are of scientific importance these days.